All right, everyone. Last video we calculated or rather found the governing equations for this system. It took us a grueling 20-something minutes to do so. If you remember, we had to draw the free body diagrams for both masses and do a force balance, and it was very tedious, easy to make mistakes, and as I promised, I would show you how to go directly to the matrix form of the governing equations in this video. So last time we started out by writing the degrees of freedom. We have two of them. When we're looking for the matrix form of the governing equations, it should look something like this. You will have a mass matrix multiplied by an acceleration vector plus a damping matrix multiplied by a velocity vector plus some stiffness matrix times a displacement vector, which will be equal to some force vector. Okay, fair enough, pretty easy. Now we have a 2 degree of freedom system. The matrices here are always going to be square and symmetrical. So let's start. All right, so for the mass matrix or the inertia matrix, it's always equal to the diagonal being the mass or the inertia, and the rest being zeros. So let me write it out, acceleration 1 and acceleration 2. In the first equation, the second mass isn't involved, so we only have mass 1 times acceleration 1. And for the second equation, we have 0 times mass 1 and 1 times mass 2 times acceleration 2. So we already have this part. Now for the damping matrix and the stiffness matrix, the diagonals are filled with the sum of all the elements that are attached to it. So what I mean by that is that, let's say for the first mass, you have C1 and C2, damper 1 and damper 2. So on the diagonal of the first equation, we have C1 plus C2. And on the next row, which corresponds to velocity 2, I'll write it out. You would have minus the element that joins the two of them. So what joins mass 1 and mass 2 in terms of dampers? It's C2. So you would have minus C2. Now I said that they're symmetrical. It's true, but let's just apply the same logic and say we're not on the diagonal, so what attaches x1 to x2? Well, that's minus C2 again. Now for the second mass, what is attached to it in terms of dampers? It's C2 and C3, so we will have C2 plus C3, and we're done. Now let's do the stiffness matrix. So we're on the diagonal. We have spring 1 and spring 2, K1 plus K2. So what spring is attached to mass 1 and mass 2? It's K2. So we have minus K2 because we're off diagonal. Again, what attaches K1 to K2, mass 1 to mass 2? It's minus K2. Also symmetrical. For the second mass, we have spring 2 and spring 3. So we have K2 plus K3 times the displacement vector is equal to the force vector. So we're done. It only took us 5 minutes. Now you need to be careful with these methods. In more complicated systems, it won't work. In this case, it does. Anyway, I hope you liked it. From now on, I'm going to assume that you know how to use this method, and in future examples where we're going to calculate natural frequencies for multiple degrees of freedom systems, then we're not going to take 20 minutes to write out the governing equations of motions. We're going to go directly to the matrix form using this method. All right, thanks for watching.